you. Okay, hello everyone. Welcome to this talk. My name is Farzane Aminmansour. I'm a PhD student at Martha White. And today I want to talk about several approaches to online learning problem and like some of the solutions that people developed over the past few years and why they are not sufficient to deal with online learning problems. And then I want to lay out an intuitive idea of a decentralized learning method for training neural networks. So let's begin. So online learning can be seen as like if a stream of data is arriving and you want to learn continuously on the sequence of data, and there are like some incremental learning approaches to that, for example, SGD. But it's also connected to two other perspectives, like continual learning and incremental learning. In continual learning, we also want to learn continuously, but we also don't want to forget what, yeah?
Like those, on the online scrolls and so on. It's like people cannot see it, so.
Oh, why?
Maybe you can reshare the screen.
Oh, good. Okay. You didn't miss much. Okay. So in continual learning, we want to learn continually, but we also don't want to forget, and we also want to adapt to the new task. And now it's not working. I can't go to next. Actually, what is happening?
It's moving again. Okay.
Oh, okay. Now you see what you missed. Okay, good. Okay, so in continual learning, the solutions usually try to prevent catastrophic forgetting, which I believe it's not a real problem because like even in human, like you forget some of the stuff, maybe it's not really good to remember everything actually. But anyhow, like people want to mitigate catastrophic forgetting, and also they want to do more knowledge transfer. That means that they want to generalize more. And also, as like Reach presented in the first slide, like sometimes people use dynamic architecture for neural networks so that they scale it up as they need. Or like, for example, like Farzane talks that people like use like replay buffer to go over the trajectories of sample more again and again. And then incremental learning, which basically wants to train, but not retrain from train on the new data, but not retrain from scratch. For example, SGD. And another perspective is like real-time processing. So in real-time processing, basically you want to update your parameter as fast as you can so that you respond faster. So basically two things are key in real-time learning. That is efficiency and latency. You want low latency and high efficiency. And the category of solutions that are trying to deal with this sort of perspective for online learning is like parallelizing backpropagation or like the data processing, either of them. And then the next one is like tracking adaptation perspectives. Like you can look at online learning as if like it's a tracking problem that the data changes, and like it might come from new like distribution of data, which means that you have non-stationarity, but you want to like track these changes over time and adapt yourself. And usually the category of solutions that people propose are like more like adaptive learning rates or like event-based methods, like they to detect if a change happened, and stuff like that. And then another one is mostly related to resource constraint problems, where like, for example, you're not having enough, like a lot of like computational or memory resources, and you want to keep it minimized. And the last two ones are related to RL, basically interactive learning, where like you have a human that sends feedback. You want to incorporate the feedback in your updates as fast as you can, like human in the loop in RL. And like adaptive control, basically you try to control the environment and also perform your updates like on the model, which is technically RL, right? So I said all these things because I just wanted to say like online learning is still like an elephant in the room. Like we're seeing it from different perspectives, but we don't really know what it is. Like we cannot draw lines clearly. So far, like the problem, like the environments that we are assuming that we are dealing with are like discrete environment. Like we assume that we have discrete time steps. So the input arrives and then some processing happens over time. And then that generates a feedback for you. It could be like if it's a neural network, it's backpropagation, you'll have to do forward pass and backward pass. But even if it's RL, like something happens, like you see something, state comes, then you have to wait. Like then you like take an action and then you see the like impact of that, like a reward or something. So anyhow, like we always think of problems as if they are discrete and we have step sizes. But what if we have more complicated scenarios? Like what if the data just comes, like a flow of data just coming, but the differences between samples, as you can see, the shade of these arrows changing very slowly and gradually. So the data is arriving, but the changes are very much slowly changing. So all of the changes are bounded, like they have a very small upper bound on them. And I'll categorize these type of problems in two categories, like either they're synchronous and high rate, or either they're asynchronous and high rate. And then I call it asynchronous. That means that the interval between data arrival changes over time. So it's also like this delta t is also a function of some other parameter that we don't know. Maybe, I don't know, God made that. I don't. So anyhow, what we know is that these two environments are underexplored or investigated, and we mostly were focused on this. And our beloved backpropagation to train neural network, which has served us a lot, is also designed specifically for that sort of environment, right? So the way backpropagation works is that the new data arrives at time step tau, and the forward pass happens, updates all of the actions, and then the gradient calculated, and then propagate all the error backward through the chain rule, and then an update happens, right? And then this happens again for the next data sample that arrives, and what you see here is that basically there should exist symmetry in the weights of forward pass and backward pass, right? And that means we have forward locking, backward locking, and update locking, right? These are all waiting times that we have to spend. Oh no. Okay. So these are all waiting times that we have to spend to perform one step of update for backpropagation. So this is a problem, this is a shortcoming. It's not going to work in online learning. It has high latency. We get to that. But anyhow, like for backpropagation, we already have some like line of theoretical proofs that backpropagation is working very well on stationary data, I.i.d. and stationary data. But in online learning, we're not really dealing with the stationary data. That's just the assumption that we are making on the problems. Data is actually temporally correlated, and they can be non-stationary coming from different distributions. Also, backpropagation prevents the networks to scale up or down easily. Like you cannot have dynamic architectures. And as I said, you get low latency because of all these waiting times. Also, you don't exploit the computational capacity of your system because of all of these ordered updates that you require. So you have low utility and also low throughput. And yeah, and also you cannot deal with continuous time. Like if the flow of information arrives and you're using backpropagation to perform your updates, basically you have to drop a lot of like data as they arrive, right? So it's probably not good for online learning. Other side challenges that like if your model gets large, then you want to distribute the computation, but you can't because everything is coupled. All the modules are coupled together, and like vanishing or exploding gradients. That's other issues. But what people have done so far as alternatives to backpropagation as a solution. So one of the categories of things that people have done is to try to parallelize this backpropagation convention in general. So here they call it 3D parallelism. It means there are like three strategies to parallelize updates of backprop. The first one is basically on data parallelization. So you have a data set, you break it into multiple chunks, and then you assign each of these chunks to multiple devices, and then multiple versions or copies of your network is being trained on multiple devices. But that doesn't really help with the streaming of data or online learning that much, right? The other two categories, like pipeline parallelism and tensor parallelism, are under the umbrella of like model parallelism, which pipeline parallelism is trying to like in the granularity of layers, they are trying to make things happen faster, like make things a little bit more parallel, but still sequential. And tensor parallelism is actually more fine-grained. They look into the computations of each layer, like what vectors or tensors or matrices are multiplied by each other. And then they try to make those computations more in parallel. But there is also a drawback to this category of solution because they also impose a lot of communication overhead for each of the updates. They're not really fast. Here I wanted to talk about like pipeline parallelization category and explain how they do that, because actually among all of these methods, I believe in them the most. But I'm gonna skip it because we don't have time. If you had questions, we can go back to it. But another category of solutions is like biological plausible learning rules. People were thinking with themselves, okay, backpropagation is good, it's doing well in offline, but it's not really good for online. But what does our brain do? Maybe that can inspire us to like come up with a learning rule, right? So there is a long list of all of these methods, and it's a busy slide. And I don't have time. I'm already going over time, so I'm not going to go into the details of these ones. The only two important lines in this slide, in my opinion, is these two red lines at the end. That is like generally the shortcomings of biological plausible learning rules can be listed as this. So they usually have high computational burden, or they use a lot of approximation. So that means that their accuracy gets diminished. Or like their training is not as stable, that you cannot scale it up for large data or large models. And like they are usually hard to implement and slow learners, and in general, they're inefficient. So it's not a solution. But the question is, what is an ideal learning tool, right? In my opinion, like it's actually a very fun question to think about. But in my opinion, I think locality is very important. And what I mean by locality is that I just brought back like our simple example of 3-layer neural network here. And I faded the other two. I want to focus on the layer L, the middle one. And what this layer sees is just the input activation and the activation it puts outside, and the input weight, output weight, and some input error to it. That's all. And there is a thin point here, which is, you can see that I dropped all the subscripts here, right? So basically, I broke the dependency on time step for layers. So basically, I'm independing this layer from the updates of other layers by dropping this step top, right? But what that leads us to is the second important property that I believe in, and that is asynchronicity. So what do I mean by asynchronicity? Assume that each pulse in this animation like refers to a forward, backward, and update of weights for each of the layers of the neural network. You saw that some of them were performing these local updates faster, forward, backward update, forward, backward update. So it was faster regardless of what other layers are doing. What does that mean? That means that each of these layers would have their own time scale. So I'm not gonna rush into like, because it might get complicated, I might get confused. But what I do is that I define a new subscript now, which is the time scale of each of the layers. And this is obviously like the index of the layer. And we can see that, for example, our forward updates would become dependent on the latest update of the previous layer, like in the time scale of previous layer, multiplied by the W, but the W that was updated in the last time step of current layer. So delta TL is kind of like atomic time, or like the atomic step of current layer time scale, right? Questions? Okay, good. And then the backward pass, also like similarly, I added all of these subscripts here that you can see. We are now depending on the time scale of the next layer for delta. And then the update will happen in the time scale of current layer TL, right? Now that we have it, does this really make sense? Well, I call this naive approach, naive AProp. And it has some challenges. Obviously, when you do something like this, you have a lot of this, you might get a lot of discrepancy due to the delay noise, right? So that discrepancy might prevent you from learning. But we want to see if this really happens or not. And like if we can find some sort of like common characteristic or behavior or something to improve it. So I call this naive AProp. What I do is that I take a neural network, I run each of the layers of the neural network on one independent thread, and then I start training the network. So each layer is performing its own update. And now I want to see what happens. So for that, I require a simple problem setting. The simple problem setting I'm using here is called piecewise random walk, which is introduced by Yang Chen and Kirby and Martha in 2019. And it's actually a very beneficial problem setting. So they defined a difficulty factor D that varies from 0 to 1. And this difficulty factor D basically defines how much correlation in the data points you have and how much drift you get. For example, if it's 0, you get a full I.i.d data, like data points, like a set of data points. But when it increases, you can see that the data points in each of these distributions get closer together a little bit, but then you get some drift in the distribution every like 30 steps, like in this example. And like you get 60.62, and you see this gets bigger and bigger. And like when it gets 1, like all of your data become very much correlated with each other in each of the distributions, but the drift gets long, like a large drift happens, right? What I want, and I think suitable for me, is like something in between. Like I did run other experiments on other difficulty levels, but for now, for this presentation, I do want a difficulty level of like 0.41, which is this one. And why I picked this? I picked that because I feel like it has like small changes in the data points, but also it has some drifts. So it captures a lot of the properties that online learning problems are like having. So maybe it's a good problem setting to use, like data to use. And then I take this data and pass it to a target network that's a black box to me. I have no idea how it is. It can be stationary or non-stationary, like can change, I mean, like the weights can change. Can be a stationary, non-stationary, realizable. comparing to my model that I want to train, or non-realizable. Anyhow, it gives me a target value, right? In this presentation, I don't even care about all other values. I just care about the very first 4 data points here and the very first 4 target values there, okay? So just trying to make things simpler and simpler to see if I can see any specific behavior in naive AProp or not. So now that I have this, what I want to observe, like I want to monitor the last layer of neural network. I want to see if I perform parallel updates, as I described earlier, how the last layer behaves in terms of its residual error and in terms of the activation it puts out, which means the prediction of the network, right? And voila. Okay, this plot is saying that this plot is basically like the prediction of the network, or the output activation of the last layer. And as you can see, there are some sharp angles here that are pointed with these blue arrows, and these are actually the time steps that the new data arrives. Okay, so I should maybe mention that I'm not moving to the settings that are asynchronous or high rate. I'm still trying to understand things better in the discrete time. Okay, so we still send the input data over the time steps tau that you see 1, 2, 3, 4, but also want to see the behavior of last layer over continuous time, or over its atomic time steps. And you can see this, right? I wanted to plot backpropagation behavior here, but honestly, it just was making things complicated, and I had to make more slides to justify why this is happening, and then that's I believe it's irrelevant to this talk right now, so I'm gonna skip that. And like this first, okay, I'm gonna get to that. So yeah,
overlapping here, right? I only see one line.
yes, because I don't show backpropagation.
Oh,
yeah. So if
Sorry, you said you had to care about just the first 4 points in that data. It's like, how does that connect to this plot here?
yes, so the first data arrives here, the second data, third, fourth.
Okay.
So there are 4 data points arriving, and I'm plotting how they are learned, how they are being learned. So yeah,
this is the error.
this is the activation of the last layer. So basically the prediction of the network.
I don't know what the true value is. It is showing me the prediction.
That's a very good question. So very surprisingly, in this problem, which is a simple problem, the true values are actually the convergence point of these oscillators. This is very interesting. This is very interesting. So if I plot the residual error of the last layer, then I would be just seeing a shifted version of those damped oscillators that are converging to 0. And there is a subtle point here, guys. Like at the beginning, like you see that the amplitude of these oscillators are kind of big, but then as it goes on and on, like here I plotted for 5 samples, right? 1, 2, 3, 4, 5, right? I plotted for 5 samples, but you can see that like the amplitude of this basically down oscillator is becoming smaller and smaller. That means that maybe your network is learning this distribution that the data is generated from, right? But we don't jump into that now because maybe it's too soon to get conclusion. Anyhow, what I want is that, yeah.
I just have a quick question. So if we go back to the previous slide, there are the 2 times.
Oops. Okay.
So just to explain the
These two?
clock time. Yeah, so are you doing like 400 updates on the first sample?
Exactly.
Okay.
Yes.
And these are from,
For the last
Right.
layer only.
okay, but and this was like from the previous slide where you have like, it's still the same, like it's just the first 4 steps of the environment. And you're just like doing a bunch of updates on the first 4 samples.
Exactly.
Okay.
Yes, that's true. I'm glad. Okay, then, okay, what I do is that I'm gonna feed a damped oscillator to these. And then I say, if I see this signal, what characteristics I can learn from the signal, okay? So I'm gonna get the Fourier transform of it and see what are the characterizations of this signal in terms of the frequencies that built this signal. So for those of you who don't remember the Fourier transform, the Fourier transform basically tells you what frequencies and what shape of signals are used, or like the combination of what signals, or like this signal is a combination of what signals with what frequencies, right? And whenever there is like a spike like this, they say it's probably due to the noise. I wanted to go into the like intuition behind it, but it takes a lot of time. I hope you trust me. When they when they want to like filter out the noise, they just pick these spikes, and then you get the inverse of the Fourier transform. And what happened? Okay, you get the inverse of the Fourier transform, like this is this like noise of this. So now I'm seeing the noise of this damped oscillator, right? Which is like, okay, maybe that's okay. But can I see any pattern here? I don't know yet. Like, you should even right now criticize me, because like maybe I was lucky that I was seeing this damped oscillator. Like maybe if I enlarge the like number of like features in the data, or like the size of or length of the layers, maybe I don't see the damped oscillator anymore. Maybe I get a diverging signal. Maybe I see a growing oscillator instead, and I never converge, right? And it can be due to like maybe two main reasons, maybe like enlarging the data or network, and also maybe the fast, like, or the big changes of environment, like sudden big changes of the environment, like the between the data samples. But let's see what will happen if I get a diverging or growing oscillator. So this is an example of a growing oscillator. I still get the Fourier transform of it. Oh, wow. I get the similar characteristic of the frequency in the frequency domain. That's, wow, interesting. I mean, we know that. And then we get the inverse of the Fourier transform, and then we get a noise signal here. But let's compare these two hypothetical growing oscillator and damped oscillator with each other side by side. So the blue one is the original signal. One of them is a growing oscillator, and the other one is a damped oscillator. And these are the noise for both of them, which seems like they have common properties, right? So if we take a closer look at this, I can see that at some points, the noise is very large. And at some points, the noise gets smaller with the amplitude of noise, right? And these red arrows show where the data arrives. So when the data arrives, and this is still for the last layer. So when the data arrives, all of a sudden it changed the value either in the input or the output. And the values are input activation from previous layer or output or the input error from the next layer, all of a sudden become irrelevant. So you get this big noise in them. And then as you go on and on, this noise become smaller and smaller, so that you can, your layer can trust the input values to it more and more. And then after that, it grows a little bit until like the next value, basically the next sample arrives to the network. And if I draw this envelope of the noise here, on the damped oscillator, this orange dashed line is basically the envelope of this noise. Then you can see that there's a cool pattern here, right? Like it's like a periodic signal that goes up and down, and like these are basically like, then you can behave like you can look at it as if like you don't trust the values at these points because the noise is too big, but then you can trust the values here because the noise is small, and then you can't trust again. Trust, no trust, trust, no trust, right? So if I do the same thing, like the same procedure for other layers, like this, our simple example, that was for the last layer, but let's do it for other layers too. Then we can see some rhyming pattern of like periodic signals on these layers, all of these layers, that sometimes we can trust them, sometimes we can't. The solid line here belongs to activations and how much we, like when we can trust the activation values. And the dashed lines basically correspond to the input errors to each of the layers. And here, for example, you can see that for the blue, which is the layer 1, the solid line is the activation, input activation to the first layer. At time 0, new data arrives. So this got updated. The activation of the first layer is perfect, no noise in it, right? But on the other hand, the dashed line for the blue, which corresponds to its error, it's fully outdated. What it's getting from the output doesn't belong to this input, so it can't trust it. But as it goes on, like these start changing. And what backpropagation is basically doing is that it performs its updates on these peaks. Basically, the data arrives, it performs a forward update here, then with a little bit of phase shift performs the next forward update, then the next forward update, and they are all perfect, highly trustable. And then we are here at the end, backpropagation, calculate the error at the last layer, so backward 3 happens with high confidence, then backward 2, then backward 1. And then one round of update is already done in backpropagation. As opposed to what we want in AProp, that is, I want to be able to update anytime. And this will give me, this will tell me how much confident I can be about my current update that I'm performing, right? So to me, this sort of rhymic pattern can be corresponding to a dynamic memory or a dynamic trace of each of these input activation or error that is coming to each layer. So when I have high noise, okay, when I have, I'm almost done. So when I have high noise, I want to not to trust the current value. So I increase the size of my trace, like the size of my memory. I see a bigger horizon in the past to average out the noise, the big noise. And then I can actually trust the updates, like the values of error, local error and activation. I perform sharp updates. I just consider a current sample, I perform an update instead of like a memory of that. So basically I can define like a trait, I can define trace of activations for each layer and trace of error for each layer. And I can treat this as like a dynamic memory for each of them, right? And then local updates of AProp, only we change a little bit compared to naive approach, which for each of the local variables that we want to keep, like we have delta bar, which is the trace of delta, and h bar of L-1, which is the trace of input activation. And then using this, formulation that I'm not writing the math for that, but like this would be the smoothing factor changes of the trace, like the moving average, exponential moving average thing. Then my update rule would look like this. So these two are basically similar to naive AProp, forward update, backward update, to calculate HL, like the output activation and delta. But I perform more updates using the traces of input activation and input and like the error, right? I use the traces that allows me to average out noise or like perform the others. And these activation traces, activation and errors also calculated based on their own like arithmetic signal for zeta delta that changed over time and zeta h that also changed over time. To recap, finally, so today I talked about online learning, and then I said what backpropagation was and why it was not enough, and like how it had several locking pairs and updates and going to the next step. And then I said I believe asynchronicity and locality are the like main properties that we should care about. And then I assume that okay, we have naive AProp, and then I just constantly perform update on multiple threads for each of the layers. And then I said, okay, I saw some properties that seem to be common from naive AProp, and then I came up with the idea of AProp, which has these dynamic memories, like dynamic traces of the path to perform updates for both activations and errors that are coming to each of the layers. And you can see that they vary like a arithmetic signal here, because they represent those arithmetic smoothing factors. And I want to say AProp solution is everywhere and nowhere. So, so it's kind of like in between, in the landscape of online learning, it's trying to deal with a lot of things, but it's also not perfect, because like these phase shifts must be precise, and like there are so many complications that we still haven't dealt with, right? To make it ready for a real problem. And then, yeah, finally, thank you guys. I'll take questions now. And I already got my first question from Warren. Like he said, this guy who looks like me in the department gives a lot of vibe of Rich Sutton. And he was wondering why, and that's why. Yay. Okay, Sheila.
How is that different from Adam? The nice places that you have.
How is what?
Do you use Adam?
The optimizer.
Oh, optimizer. It's like what? Yes, I use Atom Optimizer. Oh, maybe I should say what the network looked like. So the network I used was like a 5-layer, 4 like neuron per layer. Well, obviously scalar in, scalar out, activation celu, and optimizer Atom. Yeah.
So I was a bit confused about the outer problem that you're facing. I think the outer problem is basically you're like, in this simplified case, you're tracking a single scale.
Yes.
It's moving around. On occasion, it shifts.
Yeah.
And it's also true that there is no input.
There is input, like the random walk
There's a
is the
change
input.
target.
The random walk is the input. The output of the target network, the black box I showed here. How do we go back? Oh, too much. Sorry. Yeah, so do you remember there was a black box thing that I sent it? Is it too bad if I quit it? Animations?
Shift.
Oh, if I do shift it, oh. Magic. What you saying? I did too much. So the problem was, this thing. This thing, right? So this is a target. So this target model is something that I don't know of. This is not what I want to train. This is something that I'm not aware of, and it's just generating the target values for me. And the input to that target network is the random one. So I pass this
Into
scalar,
your learning system.
and this also goes to my learning
You
system.
really,
So it would be like prediction problem with this target and this input. So I pass this input to my network, and that would be my labels or my target space. And I'm hoping that I can somehow model this black box that I don't know what that is. Yeah.
Oh, what's your, so in supervised learning, I plot test error. If I have good test error, I'm happy. What do you plot here, or what is the final thing that you're looking at, the final performance metric?
Right now I didn't talk about that. So right now, what like I did before, like I ran a lot of experiments and lots of like different settings and stuff like that. But in this specific type, what I just care about was learn. I just wanted to show that I can learn,
Which means?
which means that I can learn. Like that means that like if I can have a decentralized learning method that doesn't have to wait for these locking phases to go in order. I like decoupled the network. I broke the dependencies, and I showed that I learned because of these damped oscillators that is happening. Yeah. So I haven't like done, like I haven't shown like okay, this is the accuracy. And by the way, I don't think supervised learning problem settings are relevant here. So like if I submit a paper and like a reviewer tells me that, hey, why didn't you do it on CFAR? I would be, I don't know, mad. Yeah, because like that's offline, right? Like you shouldn't expect it to work for all settings. It wasn't the goal. Like backpropagation is already doing very well, like offline setting. Yeah. Yeah.
So, oh,
No, you go ahead. It's okay.
so here it's like you're making multiple updates on each sample, right? And then you won't know when each sample is going to arrive.
Like my algorithm doesn't know, but I know because I made the problem still synchronous. The problem is still synchronous. Like I know what time is that the data arrives. I know the algorithm doesn't.
Right, but why should the algorithm keep updating with just the stale data? It's like seen it once, but we just keep updating over it.
It's okay. The gradient of the error becomes zero if it converges to the optimal point, right? Like it doesn't, like here, maybe
Yeah, but
it's
when you
better here. Like if it's updating layers locally, and it's already converged to the zero for the residual, then all of the errors all along the network becomes zero. Like the residual or like the error for input error for all of the layers becomes zero. So basically it wouldn't perform update anymore. It's just wasting time. But it could, like if it wasn't converging, it could continue. Right? Yeah.
But when you overfit, if you just do that, like you're doing a bunch of updates on just one sample, like you're just gonna be chasing after each sample, right?
Yeah, so basically, like, I don't call it overfit because we are not overfitting. Like, what does even mean to say I overfitted in online setting? That's not true. Like, we wanted to track, and we tracked it very well. It was perfect. Like, we tracked it with zero error, right?
I mean, do you want to?
So I mean, overfitting is relevant with when we are talking about like supervised learning, when we want to like just model everything all at once because everything is I.i.d and irrelevant with each other. But like in online learning, it's just things are gradually changing as around us. Like I don't all of a sudden disappear and appear like in the middle of Jasper that is burning, right? So it's too much changes. Like I have to get the car slowly go there and like adopt myself as I go, like adopt my brain as I go, and like start adjusting my predictions. Because when we think, it's not that you say something and then I perceive it and then I say, okay, I understood this. No, you already predicted that what you perceived was the prediction. You already predicted the prediction. So there's two different things. So we don't really want to, we don't have overfitting. That's what I'm trying to say. Yeah. We want overfitting. That's the goal. Yeah.
I don't think if I correctly or not, but I was kind of curious about when you say, for example, we have some robust variables for the noise, and based on that, I can make some cross.
Right.
So, for example, kind of
Yeah.
overcome that noise. I was curious if that invariant frequency for the noise is invariant with respect to the task or the problem.
That's true. I actually, yes, I wrote this. I didn't talk about it. I'm glad you asked the question. So basically, this shape of noises and like this envelope, this arithmetic envelope that we see, is related to the characteristic of our hardware, like our brain, like and the task. For example, the number of flops you have to do in one layer, and the number of cycles of the hardware to process these number of flops are two factors that are fixed, right? So every time you send an input, usually the bandwidth doesn't change. Like it doesn't, like all of a sudden in real life as a human, it's not that I see with better resolution and one day I see with worse resolution, right? So the size of the input is usually fixed. And the size of the network is also usually fixed, like the layers. And the number of cycles per processor is also fixed, like the computational power of the processor is also fixed. And the number of flops is also fixed because all of the things are fixed in the environment in terms of sizes. So because of that, we can expect to see similar patterns all the time. We can expect to come up with some precise thing here. And actually, I had two more slides after, but I removed them because of the time. But like in the discussion and like future work, I mentioned that like one of the immediate future work could be that to learn the precise values of these envelopes somehow. And then after you have that, then you can confidently use them for performing your updates. No one else? Oh, let's see. Online question here.
Hi, Farzane.
Oh, there is someone online, and I don't know where is my Zoom. Oh, sure. But I
Can you hear me?
hear you. Who are you?
I'm Mehran. Great presentation, by the way. Yeah.
Oh, thank you.
And
Sure.
I just had a quick question, like the one factor of efficiency here for like using asynchronous updates is the factor of like how much time it takes to learn. Like, is it like how much it is faster than backpropagation? Did you do any kind of analysis?
It's not faster. It's not faster at the moment. Like for now, to get this damped oscillating behavior, you need to actually clamp the input and target for a while for the network to converge to that data point. So in terms of like global time, AProp takes more time. But the hope is that in a real online problem setting, when you have synchronous high rate or asynchronous high rate, those two under investigated in problems that I talked about before. The hope is that in that sort of problem setting, it shows some it shows some advantages over Backprop in terms of time and performance. And the reason is that when the data comes as a flow, I still can get a trace of the input. So I can contribute the information of all of the data that Backprop is probably gonna miss, and I can contribute it to my updates. But backpropagation can't, it just drops all other samples. So I'm hoping that in those two settings, AProp can do better, actually. This is a lot of work to get there. Yeah. But right now, no, it's not good. Like my goal wasn't the time.
Thank you.
Yeah.
Thanks again. Thank you.
Thank you.